Hi. We're going to talk about finding areas, but not the usual kinds of areas. Finding the area of an object with straight sides, a square or a rectangle, or something that's a little more complicated, is relatively easy because all we have to do is to take this rectangular area and break it up into smaller bits. All right? And then we can sum the areas of those pieces. Even if it's not an ordinary polygon. All right, there's a polygon with 10 sides. I can break this up into triangles. All right, and so I can find the areas of all these individual triangles and add them up. But finding the area of something as simple as a circle, well, we know how to do that. That was my compass going around there. All right. We have a formula that says that the area of a circle is pi r squared. Well, where on earth does that formula come from? Well, that formula comes from a limit process, the same kind of limit that we've been learning about in calculus. And that limit is if I divide this thing up into lots of triangles, I can make them all the same size. Right. And if I continue around like that, I'll get an approximation of the area. And as I fill in more and more of these triangles and make them smaller, right, the area, and we could actually do this, we're not going to do this right now, would be the limit as the number of rectangles or number of triangles approaches infinity, the sum of the triangle areas. And that's what leads to this formula, okay, pi r squared. And that problem is well within the limits of what we can do with the calculus we already know. All right. In this section, section 5.1 in our textbook, we're going to look at the area under the graph of a positive function. Okay. So I've got some function y equals f of x. All right, maybe this function describes a semicircle, and then I would be back at the circle area problem. And I want to find the area under this curve between a and b. So in particular, I'm looking to find this green shaded area here. All right. How do we do that? Well, we're going to proceed as we did with the circle. We're going to chop this up into smaller pieces. Right. And the way we do this is we're going to divide the interval from a to b into smaller subintervals. I'll just pick a few here to illustrate. We'll get into the details more on the next page. And it's convenient to make these all have the same width. All right. Now, finding the area of each of these strips is really no easier than finding the area underneath the entire curve, because each one of these has a curved top boundary. But now what we're going to do is we're going to approximate the area of each of these strips by using a rectangle. Right. So for instance, I might choose to make a rectangle here that's kind of an average height, and in here, and then here. And how we pick these particular rectangles is something we'll explore, but we're going to get a sum of a bunch of areas. Right. And each of those rectangular areas I can find pretty easily, because calculating the width here, that's just the length of this range here, a to b, divided by the number of intervals I want. So I know the base of each rectangle. And the height of each rectangle I'm going to get by picking an x value and evaluating the function here to get the y value. All right, so that's going to give me the height. And once I have base times height, I can find the area of the rectangle plus the area of the rectangle and so on. Right? And the area will be approximately the sum of the rectangle areas. So far that's not a calculus problem. But what makes it a calculus problem is now we're going to say let the number of rectangles here go to infinity. How does this area behave in the limit as we take and divide this interval into more and more smaller subintervals? All right, on the next page here we're going to get into the notation. So same problem, I want to find the area underneath the graph of some positive function. All we require is that that function be greater than or equal to 0, at least on the range that we're interested in. And what we're going to do is divide this into little subintervals, all having the same width for simplicity. All right. So the way we determine the width of each of these subintervals is we're going to say delta x, or the change in x, or the width of each subinterval, that's equal to the length b minus a divided by the number of these rectangles I want to make. So in here is the number of rectangles. And then we're going to label these points. This is the 0th one, and the first one, and the second, and the third, and so on, until we get to B, which will be the nth point. All right. So A we could also label as x0, and B we could label as xn. All right. And now we're going to divide our area into strips. And the width of each strip we've already determined. We're going to call that delta x. All right. I need to take and find a rectangle here. So what I'm going to do for each strip is pick some point in the interval. It can be the midpoint, the left point, the right point, any point in between. And I'm going to label this one x1 with an asterisk, or x1 star. We'll call that a sample point. The sample point is used to evaluate the function. All right. So this point on the curve right here has coordinates but the particular thing I need there is the height. Right? The height is the function value. Okay. And so this red rectangle right here, which is about the same as the strip, right? So the area of rectangle 1 is base times height, or delta x times f of x1 star. Now x1 star is just some point you pick in the subinterval where you're going to use that point to evaluate and find the height of your approximating rectangle. All right. Now I need to repeat this for all the different rectangles, all n of them. And when I'm all done, I have a formula that says the area is approximately the sum of the rectangular areas okay. This is equal to delta x times the height for the first rectangle plus delta x, the base, times the height for the second rectangle. And I have to do this for all n rectangles. All right, writing that notation gets cumbersome after a while, so we frequently in this section and the next section are going to use summation notation. So a shorthand way to write this, and if you don't remember this kind of notation, you might want to go back to the appendix at the end of your book. I think it's Appendix E, and review summation notation. Right. So let me write it down here and then I'll say what it means. This means I want to take the sum as I ranges from 1, that's the beginning index, to n, the ending index, of the height of each rectangle, so that's the function evaluated at the ith sample point, times delta x. So this summation notation means it's just shorthand for this whole business right here. Right? We need to let I be 1, and then 2, and then 3, and then the sigma here means add up those quantities. Okay. Just a quick example of some summation notation. For instance, if I had I equals 1 to n of 2i squared, that means I need to take 2 times 1 squared plus 2 times 2 squared plus 2 times 3 squared, all the way up until I get to whatever n is. So I'd have 2 times n squared. We're going to be seeing sums like this throughout this section and the next section in our textbook. Let's look at a particular example. what I want to do is approximate the area under y equals x squared on the interval 0 to 2 with 4 rectangles. And we're going to do this a couple different ways. We're going to, when we go to choose our sample points, we're going to use left endpoints and right endpoints and a couple variations on that. All right, and we'll see what that means as we go through this example. So a picture is usually helpful. We're going to draw a parabola here from 0 to 2. And we're going to divide this range into 4 subintervals, and it's easy to label what those are going to be, where those points are. So this is A, x1, x2, x3, and B. Okay. Now we have 4 strips. All right. Now the sum of the areas using right endpoints What does that mean, right endpoints? Well, on each subinterval, when we go to calculate the height, or when we choose our sample point, we're going to choose the right endpoint of the subinterval. So for this first one, we're going to evaluate the function at 0.5. Right? And of course, that gives us a height of 0.5 squared. And here we'll have a height of 1 squared, 1.5 squared, 2 squared. And right here, if we ever should need it, we'll have a height of 0 squared. Let's just write those down. So that's height 0, of course. 0.5 squared would be 0.25. 1 squared is 1, of course. 2.25 and 4. So those are the heights that we might need where we evaluate the function. Right. So the area is going to be approximately, we'll call the right endpoint sum R and then 4 because we're using 4 rectangles. Right, it's the width of the first subinterval, 0.5. Say delta x times f of x1 plus delta x times f of x2. We have to do this 4 times until we get to the 4th point. The 4th point here is the same as b. Okay. So this is 0.5 times the function at the right endpoint for the first interval. So times 0.5 squared plus the width times 1 squared. So we're evaluating the function at the right endpoint of the second interval, plus 0.5 times 1.5 squared plus 0.5 times 2 squared. Right. It's not hard to figure out that this sum adds up to 3.75. Right. Does that under approximate or over approximate the area? Well, if you think about it, since let's draw these rectangles. We never drew them. If I'm using the right endpoint, right, then I'm using the endpoint at the right end. So each of my rectangles is over the top of the curve, and I can see that easily since this function is increasing. Right. So this is an over approximation. Too big. Right. Let's try it again using left endpoints. Same idea, but for each subinterval, what I need to do is use the left endpoint. So for the first subinterval, right, it's the same idea. I'm going to have the width of each interval times f evaluated at some point, and I need to add that up for all the subintervals. For the first interval, right, from 0 to 0.5, I use the left endpoint to get the height. So I'm going to have the width 0.5 times f at 0 plus the width 0.5 times the left endpoint of the second interval, f of 0.5, plus 0.5 times the function evaluated at 1 plus 0.5 times the function evaluated at 1.5, because 1.5 is the left endpoint of my last interval. So this is 0.5 times 0 squared plus 0.5 times 0.5 squared, etc. I'll shut up. Pick up your handy dandy calculator, and this sum comes out to be 2.75. Okay. Now this one is an under approximation. Let's look at our picture. Right. So if we use the left endpoint, this is our height, and our rectangle now is complete. It collapses for this first subinterval because it has 0 height. Left endpoint here, find the rectangle, find the rectangle. So because our function is an increasing function, each of our rectangles falls under the curve. Right. So now this is an under approximation. Okay. So what we can say is the true area is somewhere between the upper bound, the over approximation 3.75, and the lower bound 2.75. It wouldn't be a bad idea to average these two. And if we did that, if we add them, divide by 2, we'll get 2.6875, which is very, very close to the actual area. All right. How are we going to find the actual area? Well, what we'll see on the next page is that what we're going to do is divide this into more subintervals. Right. So if we chose 8 of them, we'd have 8 strips, and we'd have 8 terms in our sum, or 16, or 50, or more. And I'm just going to summarize those results for you with a little table here. I guess it should have been pre-written, but let me just sketch it out real fast. Now, right and left endpoints are not our only choices. Right, we could also go here and pick the midpoint of each interval. Okay, so for instance, between 1 and 1.5, I could use my sample point to be f of 1.25, right? And that would be my rectangle. So that might be called, that's called the midpoint formula. All right, I'll call that n, big M, with the subscript n to represent how many rectangles we're going to take. All right, now let's just report some results here. And after that, we'll pretty quickly see a pattern. On the previous page, we saw that I misreported a couple of results there, excuse me. All right. Back here, if you actually went to calculate this sum, you would have found out that it's 1.75. I messed that up. Okay, so 1.75 here. And then averaging those still gives us the correct number there. My bad. Okay, so if you were checking this and didn't get the same answer, sorry about that. Now it's fixed. All right. Using midpoints, we get 2.625. When we increase the number, when we double the number of subintervals, using midpoints, we get 2.6525. Now, the left endpoints, we know those are always an under approximation, so these numbers are increasing towards the actual area. These numbers are going to decrease because they're over approximations, but we're going to get better and better as we increase the number of rectangles. How about the midpoints? The midpoints are more accurate. By the time, I don't remember what this one comes out to be, but by the time we get to the 100th one, right, which is essentially the answer to several digits. All right. So when we take infinitely many rectangles, when we solve the calculus problem of taking the limit as the number of rectangles go to infinity, we find out that the actual answer here is 2.666, or 8/3. And each one of these is going to converge to the same answer. They're all different approximations to the same answer. And as we choose infinitely many rectangles, we're going to get the same answer for all of them in the end. All right. Let's look at this limit idea just a little bit. Okay, so back to our picture. Divide into equal width subintervals. Okay. Each has width delta x. Which is the length of the whole interval divided by the number of subintervals. From each subinterval, choose a point, midpoint, left point, right point, any point, and evaluate the function at that point to get the height of that strip, or the approximate height of that strip, and then imagine a rectangle through that point. Right. So the actual area is what we get when we increase the number of rectangles toward infinity. What is the limit of that process? So the limit, as the number of rectangles approaches infinity, of the sum of the n rectangle areas. So this is the limit, as n goes to infinity, of, there's the area of our first one, plus the area of our second rectangle, approximating rectangle. And we're going to start with n of these, but remember n here is going to increase. Alright. Now writing that more compactly, we're going to use our summation notation here. Summation notation might be a bit awkward for you, but you're going to have to get used to it over these next couple of sections. We're going to use it quite a lot. So again, if you're having troubles remembering or about summation notation, go to the appendix in your textbook. There's a review there. So this is the definition of the area underneath a curve, at least a positive curve. Right. Now this isn't a very practical definition if I need to sit down and evaluate something, because, well, what are my xi stars? What points are those? And I got to put my function in there and work with it and so on. All right. So we're going to take this formula here, all right, and we're just going to work with right endpoints of our subintervals. All right. So how do I get these right endpoints? Well, the right endpoint of interval I, right, so the first, the second, the third, and so on, is just x sub I. All right, we start with x0, x1, so the right endpoint is x1, the right endpoint of the second interval is x2, and so on. Right. And how do I get to the ith point? Well, you can think of that as starting at the first point, A, and adding delta x I times. We know what delta x is, so this will be a plus I times b minus a over n. All right? And I'm going to use those right endpoints as my sample points, right, to make a simplified version of our formula here. Right? So this is going to become our sample point. Right? So we're going to put that in here for our sample point. Delta x, we're going to use our formula right here. Right? So using right endpoints, it's not the only way to do it, but it works. We get the area is equal to the limit as n goes to infinity f of xi, so f of a plus I times b minus a over n. And this is the complicated bit. This means we have to take this kind of abstract looking thing here. Maybe we've got numbers for a and b, but n is not determined because we're going to let n go to infinity, and I is not determined because it's related to n. We have to take this complicated bit here and plug it into our function. And then we have to multiply by the delta x, the width of each subinterval. Right. Now notice that this part here doesn't depend on I in any way. All right, so I can factor it out of the sum. So we're writing down here a formula that can actually be used to compute one of these areas. And we're going to see on the next page that's exactly what we're going to do. Alright. So now we're going to use this and apply it to the area under a parabola problem that we saw just a page or two ago. A lot of notation in this section, so this is maybe kind of a long video, but if you want to know what's going on, you just pay careful attention. All right. So we're going to find the exact area under y equals x squared on the interval from 0 to 2. So we don't have any formula from geometry that would tell us what that area is, but calculus comes to the rescue. Right. So the area is the limit, excuse me, as n approaches infinity of the sum of the approximating in rectangles. Now here we're going to use our computational formula with a equals 0, b equals 2, and f of x is the function x squared. Right. So we're going to have the limit. I'll just write down the computational formula again here. So, and then we'll substitute into it. So b is 2, a is 0, so we get here the limit as n goes to infinity of 2 over n. These limits are kind of awkward and take a lot of work to get set up. All right, so we'll see later in this chapter that there's a shortcut way to find this area that's related to antiderivatives. And some of you who've had calculus before already know about this, but you're still responsible for knowing how to do this process. Just like you're responsible for knowing the definition of the derivative, you're responsible for knowing the definition of the area. All right, so this is 2 over n times the sum. I don't need that 0, so I'm going to just write this one more time like that. Now I need to evaluate my function at this point. Well, my function takes a number and squares it. So now Patrick JMT will be useful here for looking at more examples of doing these kinds of sums. Feel free to hit him up on YouTube to see what you can find. So my function takes my number and squares it. So I get I squared times 4 over n squared. And this 4 over n squared doesn't change with I, so it's a term, it's a factor in every term in my sum, so it can be factored out. So I'm going to write this. Alright, and now we need a shortcut. What does this sum represent here? It represents 1 squared plus 2 squared plus etc. plus n squared. Alright, and you'll find in your textbook that the textbook provides a table of shortcuts. It's actually in section 5.2 where they're listed. And those shortcuts look like this. If I want to add up the sum of the first n integers, or the sum of the i's, here's the shortcut. The sum of the squares, here's a shortcut formula. You don't have to memorize these. The sum of the cubes, right, looks similar to this, but again, you don't have to memorize these formulas. They'll be provided for you on an exam or a quiz should you need them. Right? You just need to know how to use them. So for this example, I need to use the sum of the squares. And if we go back and look at that formula, it's n times n plus 1 times 2n plus 1 over 6. Okay, now h6 there, that's 4/3. I can bring that outside the limit. And I'm not going to FOIL this guy out all the way. I'm just going to observe here that if I look at the leading coefficient, this is a cubic polynomial, it's going to be 2n cubed plus some other stuff, which I don't really care about because down here I'm dividing by n cubed. Alright, so some of you know the trick that you can look at the leading coefficient, or you can divide through every term here by n cubed, but the value of this limit is going to be 2. Alright, so we get 4/3 times 2 is 8/3, or 2.6 repeating. Right. This is what we claimed the actual area was on a couple pages ago, and now we've seen using limits that this is exactly the area underneath the curve y equals x squared on the interval 0 to 2. So this area is 8/3. Right. So again, finding areas comes back to a calculus idea, the idea of finding limits. What we're going to do here in a couple of seconds, we're going to hook up this idea of calculating a limit to what we've been working with, antiderivatives. And that's called the fundamental theorem of calculus. We'll get there quickly enough. All right, one more kind of problem and then we're done with this section. So we have a runner. Is accelerating. This is similar to problem number 13 in your text. So at the beginning of a race, and we're going to write down her velocity in 5-second increments. All right, so we have her at the time t in seconds, we have her velocity in feet per second. At 0 seconds she hasn't started yet, so her velocity is 0. So we have some snapshots of her velocity. I mean, we use a radar gun to get those. All right. Now what I want to do is approximate how far she actually traveled during this first 3 seconds. And we're going to get an upper estimate and a lower estimate. So how far did she go? Well, the upper estimate, what I'm going to do is look at each subinterval. Right? So the distance is going to be the sum of the distances on the subintervals. And how do I find distance? Well, distance is rate times time. So I'm going to look at this first subinterval. All right, the time for that first subinterval is clearly 1/2 of a second. What was her velocity? Well, since we're trying to get an upper estimate here, I'm going to use her maximum velocity on that interval, which is 7.4. So for the first subinterval, we have distance is rate times time, and we're getting the upper estimate here, so we're going to use 7.4 feet per second times 1/2 of a second. For the second subinterval, her max velocity was 12.6, and she had that velocity over a period of 1/2 a second. Okay, and then 15.7 for 1/2 a second, and so on. 17.7 for 1/2 a second. On the fifth subinterval, her max velocity was 19. We'll use that velocity for 1/2 a second. This is an overestimate because we're using her maximum velocity on each subinterval. Right? And if you do the math there, it's not hard to check that. Right? We have here feet per second times seconds. The seconds cancel, and so we have 7.4 times 0.5, or 3.7 feet. If you add those all up, we get 46.2 feet. Okay. A lower estimate for her distance traveled is similar. All right. Except what we're going to do is on each subinterval we're going to use the slowest that we know she was going. So on this first subinterval, she traveled for half a second at 0 feet per second. So we're going to have 0 times 0.5. On the second subinterval, all right, the slowest she was going was 7.4. So we're going to use 7.4 as our underestimate. So it's all the same terms that we had, or mostly the same terms that we used in the previous sum. For the third subinterval that goes from 1 second to 1.5 seconds, her minimum velocity was 12.6. And I'll write these all down here just to be thorough. And notice that these terms are all pretty much replicating what we had until we get to the last subinterval. On the last subinterval, 19 to 20, we're going to use the slowest speed, 19 times half a second. So for the last subinterval, the 20 never comes into play. Right. That's okay. Right. If we add these up for a lower estimate, we get 36.2 feet. So the true distance she's traveled is somewhere between these two numbers. We could average these together. Right, and that would give us about 41.2 feet, which is remarkably close. All right, the actual distance she went, I got these numbers using a formula, and when I added everything up for that formula using infinitely many terms in my sum, I got 41.5 feet. Okay, how is the velocity problem that we just looked at here related to the area problem that we were doing before? Well, what's the connection? All right. So here I've drawn a graph of this velocity. So here's the velocity in feet per second. Remember, at 3 seconds she was going about 20 feet per second. At 2.5 seconds about 19, and so on. There's some small problems with scale in this graph, but we'll get over it. All right. If I want to figure out how far she's traveled, all right, what do we do? Well, to get the overestimate, we went to the first subinterval. So on this axis, we've got time in seconds. We said the length of time that was elapsed was half a second, and her approximate velocity was the velocity at the right endpoint, right, which was 7.4. Right. So the velocity that we used was this times the time elapsed, which is this distance. That's an area of a rectangle, right? And for the second one, we used the velocity here, which was 12.6. That's the area of a rectangle. So our overestimate was the sum of the rectangles, sum of the areas of the rectangles using the right endpoints. Okay. The lower estimate, well, we used her smallest velocity on each subinterval. So we used the left endpoint. Because she's accelerating here, the smallest velocity always occurs at the left end. Right? The thing to recognize here is the distance she travels, all right, on each of these subintervals is essentially the velocity, all right, which is this height times the time elapsed. Right? So it's height times distance, or height, it's y times x, it's the area of each of these rectangles. Right? The total distance is equal to the area underneath the velocity curve. All right. And that's going to be a common theme that we're going to use over and over as we move through Chapter 5.